This is an example that shows the application of electrostatic potential in electricity and magnetism of a conducting sphere. How can this potential be expressed in terms of Legendre polynomial? The problem here is the conducting sphere is embedded in a uniform electric field. The sphere has a radius r0 and the uniform electric field E in the negative x direction, so that E equal minus E0, which is a constant, by k hat. The potential of on the sphere, the potential as a function of r and theta, is expressed in this way, where AL and BL are needed to be found. We need to know whether, after finding the special solution, whether the boundary conditions are satisfied or not. Obviously, to solve such system, it's very important to extract the boundary conditions from the given problem. Here we have two boundary conditions actually. At r equal r0 on the surface of the sphere, the potential is 0. And at r greater than r0, the potential is constant, which is equal to E0 z. To find the potential anywhere as a function of r and theta, we need to realize that this system has an azimuthal symmetry, which requires putting m equals 0 and cosine phi equal 1, because the potential is constant at theta. This condition, simplify the problem of the associated Legendre polynomial, which will be tackled later on, and reduce it to a problem of Legendre polynomial actually. By all means, if you want to find this solution, actually we have to solve the Laplace equation. But we're not going to do this now. We're going to do later on when we tackle the chapter of partial differential equations. And here we're going to show how can we apply the boundary condition to get the special solution out of this general solution. Now, again, the boundary conditions are at r equal r0, the potential V equals 0. Obviously, this implies that AL in the sum r0 to the power L plus BL r0 to the power minus L plus 1 equals 0. And this will give BL in terms of AL equal minus AL r0 to the power 2L plus 1. Such that when you substitute this into our solution, substitute the ladder equation or the ladder expression. Let's call it 2. If we call this equation into the first equation, we call it 1, which says phi of r theta equals sigma L equals 0 AL r to the power L, and this multiplies by B plus BL plus BL multiplies by r to the power minus L plus 1 BL cosine theta. This is our original equation, which is, we call it equation 1. From this equation, actually, by applying the boundary condition, we get this condition. Now, when we substitute this in here, we get, this is equation, we get the following. We get V r theta equals sigma L equals 0 to infinity AL r to the power L minus r naught to the power 2L plus 1, and this multiplied by r minus L plus 1, and then PL cosine theta, and we call that equation 3. So this is the first boundary condition. The second boundary condition, we have r greater than r naught. That gives the potential as given in the problem equals minus E naught Z. So in such case, the second term in parentheses of equation 3 will be reduced to 0. And here we have E naught Z equal sigma L equals 0 AL r to the power L PL of cosine theta. Or this means, when this reduces, this means that r naught to the power 2L plus 1 r minus L plus 1 approach 0, and this gives this result. Okay? Now Z equal r cosine theta, so this can be written as E naught r cosine theta equals sigma L equals 0 AL r to the power L PL cosine theta. Now what we need to do, we have to find all the ALs, but obviously here we can deduce that the only A that survive, that with the order of r power 1. So the only order of L equal 1 that will survive in the summation, because we don't have any corresponding coefficients related to the power r to the power 1 apart from this one. So to find AL, obviously, according to the legendre series, to find AL, we usually do that. We usually write this. We multiply both sides, as you know, by, and then we integrate from 0 to pi E naught r cosine theta PL cosine theta sine theta d theta. We apply the rule, and for L equal 0, we're going to get A0 equal E naught r over 2 from 0 to pi cosine theta sine theta d theta, which is obviously give us a result of 0. The L equal 1 is the only coefficient that survive here. It's going to give us 3 over 2 from 0 to pi cosine square theta sine theta d theta. When we put cosine theta equal x and take the limits for theta equal pi, this give us x equal minus 1, and for theta equal 0, this gives us x equal 1, and make the change of variables where dx equal minus sine theta d theta, and substitute this back into this formula. We can call this 3 and call that 4, and we substitute all these, which is 5, from 5, equation 5 into equation 4, we get A1 equals 3/2 E naught x cubed over 3 from -1 to +1. This is nothing more than E naught. Nothing more than E naught. And then if we apply the same formula for L equal 2, we're going to get A2 equals 0, and you can check that at home. So the only term that survives, the only term, as we said before, that survives is that of L equal 1. Thus, the final result, we have here V as a function of R or theta equals E naught R minus E naught R cubed, R naught R minus 2, P1 cosine theta. If we factor this out, E naught and E naught cosine theta, we're going to get R minus R naught cubed over R squared by cosine theta. Oh, of course, this last result, we can check that this final result satisfy the two boundary conditions, which are 1, R equal R naught, we're going to see that V naught equals 0, and the second R greater than R naught, greater than R naught. This is going to give us V equal minus E naught R cosine theta. And here is the solution. Thank you.